molecular imaging. That's kind of along the line of the sensor, but using the imaging approach. And other related nanotechnology enabled are like drug delivery, biochip high throughput screening technology. So that's today's talk. Main focus is on nano-improved lab-on-chip devices and biomolecular sensors. So since we talk about biosensors, we start with the fundamentals of the biosensors. So biosensors, we deal with a lot of samples. We start with human samples like blood, stool, body fluids, and we do the cell culture extract, the analyze that we would like to detect. And we have like a surface, and that's bind with bioreceptors, and bioreceptor can be all kinds of different molecules like antibodies, aptamers, and these bioreceptors will bind with analyze and then give you a signal that can be transducted and sent through. So you can receive either electrical signal, optical signal, so you can detect a binding event. So that's how the biosensor works. So in our case, we mainly, in our first part, we mainly focus on electrochemical biosensors. So the electrode is our interface. The surface will be our electrode. We will focus on point-of-care diagnosis. So what's the current state of the art is that now currently we normally do the point-of-care using desktop-sized devices, which is kind of computer size or that even larger than the computer size. So it's not really portable. So once you would like to bring the point-of-care diagnosis on the field bedside, it will be a little bit tough. So in the future, we would like to bring these handheld devices so that the signal can be detected right away. So in order to achieve that, there are several challenges. The first is normally the desktop size diagnosis is equivalent with fluorescent reader, and normally that is very expensive. So the opportunity that we come up with is we develop biosensors. So in this talk, we focus on electrochemical biosensor and surface plasma resonance biosensor, which is portable, so that kind of overcome the challenge of the cost of the device. So the second challenge to move on to the point of care diagnosis is the sample preparation. So as you know that when we deal with sensors, not only the signal transduction, the sample preparation is the key step. It always is the bottleneck of the whole biosensor development. So sample preparation and detection is very hard to be integrated. So in this challenge, we have two approaches. We first focus on the biosensor development, which we develop more robust biosensor. We will talk about that when we construct our biosensor. And the next challenge for the biosensor is that when biosensor, we want to move it from desktop size to the portable care, is shrinking in size. And when it's shrinking in size, the reaction is much slower, so it's more diffusion limited. So we want to overcome the diffusion limitation, so we will touch that as well. So that's our whole kind of idea. So we want to develop point-of-care oriented biosensor that has all these characteristics of the biosensor. We want, of course, sensitive, specific, response, reproducibility, all those good properties of biosensor. And our key technology is based on nanotechnology. And in our nanotechnology, we have a few bulletin points. We start with the single domain antibody. So it's a binding entity. And we use gold nanoparticle approach, and we use nanopattern electrode. So we focus on the first three for the C deficit detection, but we will also touch the point on aptamer magnetic nanoparticle at the end of the talk. So that's our focus of the talk today, C deficit detection. So C deficit infection is a very serious infectious disease in the hospital, especially for old people. So when old people is in hospital, they are very easily kind of get contagious with this kind of virus. And you can see that along the years, the number of cases has been increasing dramatically. So it's a serious problem that hospital needs to come up with approach that can faster diagnose the C. difficile infection. So what's the current state of the art diagnosis methods? As you kind of browse through this table, you can see a lot of methodologies. So let's kind of, because this is very important slide, so I want to go a little bit slower so you understand what is the current state of the art, and then we can talk about, so the test can be divided into like toxin testing, so that's more molecular based, and organism based. So when we use the toxin, the first approach is the enzyme immunoassay. So that's a very current standard assay, like a lot of hospitals use the enzyme immunoassay, which people also call it ELISA. So it's pretty fast, and it's pretty simple, and it's very low cost, but it's not very sensitive. And some only detect toxin A, so it's not very kind of sensitive method. The second method is to detect the cytotoxicity. So it's more sensitive than the ELISA, but it's very label intensive, so it needs a long time to get to the result because you need to culture the tissue. And also needs special equipment. So that's the molecular-based testing. And the second big category is organism-based detection. So organism-based detection, we have detection of glutamate dehydrogenase. So that's rapid, sensitive, and that's the normally current approach for screening the C. difficile toxin. But this method is not specific. So normally what people do is that they do the glutamate dehydrogenase detection first, and then they need to go back and do the toxin detection as well. So kind of two-step method is needed. And the polymer chain reaction PCR approach, you have heard a lot about the PCR approach. So PCR approach is very exciting. It's rapid, sensitive, and can detect the toxin gene in a very fast fashion, but the downside of it is very costly, and you need very special equipment to do, and sometimes it's oversensitive that it does not fit like the cost needs of this kind of toxin detection. So the other approach is the stool culture. So it's also a very label intensive method because you need to culture it and wait for the bacteria to grow. So it's normally a tedious procedure. So with all that, it indicates that currently there is not a very good approach to actually diagnose the C. difficile yet. So in our approach, we shift to the electrochemical approach. And in the electrochemical approach, specifically, we focus on the electrochemical impedance spectroscopy. So the normal electrochemical approach, normally they use cyclic voltammetry or amperometry. So in that approach, normally you need an electroactive tag, and normally enzyme is involved. So that's, again, a kind of a little bit tedious, long process approach because you need to assemble a lot of layers, and then you need that label to give you the signal. While the electrochemical impedance spectroscopy is label-free and is a non-destructive approach, so we choose this method over the other type of electrochemical approach. So impedance biosensor, that's the basic principle. So what you do is that you assemble the antibody and antigen on the surface. Yeah, so you assemble the antibody antigen on the surface. So it starts with a small impedance circle, which indicates the resistance is smaller. And then when you assemble more target onto the surface, then the resistance becomes larger to the electrode. So that semicircle becomes larger. And then in our approach, we put on the secondary antibody to with the gold nanoparticle to amplify that effect, the surface resistance effect. So the advantage of using the gold nanoparticle is because all the advantage of biocompatibility is very easy for surface modification, and it has, because of, as you can see, it has a lot of antibody bind to the gold nanoparticle, so it enhances the number of antibody that is bind to the gold nanoparticle. So that's our approach for the gold nanoparticle-based electrochemical impedance biosensor for the C deficit detection. So we start with the gold electrode, and then we assemble the sulfide layer. So we do a single molecular assembly, and then we put the antibody on the electrode, and then we kind of block the non-specific binding of all the empty spots on the electrode with the BSA. And then our antigen reaction takes place, which the toxin comes in to block the surface, so you read the electrochemical signal. And we put the secondary gold nanoparticle bind antibody to further enhance the signal. So it's a sandwich type, and gold nanoparticle we synthesized are within the size of 13 to 15 nanometer, and is for signal amplification. So that's the result of the whole binding process. As you can see, that's from step 1 to step 5, and you can see the cyclic voltammetry. It starts with the Bell gold, so it has a larger electrochemical activity. As the process goes through the whole binding process, it further and further blocks the electrode, so you see less and less electrochemical signal. It reflects both on the cyclic voltammetry and electrochemical impedance spectroscopy. So that's our EIS data. And the Nyquist plot, which is again the electrochemical impedance spectrum, gives you the concentration dependence when we add the toxin onto the electrode. So we go through 0 all the way to 100 picogram per milliliter for the biosensor. And you can compare that if we don't do the secondary antibody, then the signal strength is much smaller than when we amplify the signal with the secondary gold nanoparticle bind antibody. So it's a comparison of our developed C deficit detection with other available C deficit biosensor in the literature. As you can see that our biosensor using this method achieved a 0.6 around for toxin A and 0.6 for toxin B as well. So that's our limit of detection. As you can see that other approach, like cell-based, is around 1 picogram, and DPV is about 0.7, and the cell cytotoxicity is 125, which is much larger than our biosensor performance, which is our biosensor is much superior than the other type of biosensor. So a little bit summary for the first approach. So the first approach is sandwich type electrochemical impedance immunosensor, and the antibody that we use is single domain antibody. That's a special type of antibody that gives you a shorter length and a strong binding characteristic. So the method achieved a very low limit of detection, and it's very sensitive, low cost, and convenient. So you can see that it's both nanotechnology enabled. So the first approach that we have just presented is based on the gold nanoparticle approach, which they amplify the signal by binding to the toxin using the secondary antibody. Well, in this approach, you can see that it's nano-patterned electrode. So what we do, all this procedure is to make our electrode nano-patterned so that we don't need the amplification of gold nanoparticle bind secondary antibody. So that's the whole goal of this second approach. So the second approach is based on the soft lithography. As some people of the department probably already know the fabrication process. So basically you start with the silicon mold, and then you transfer it to the PDMS, and then you have a soft surface-based nano pattern. So after the PDMS, what we did is that we cut it into this specific shape. So the purpose of this specific shape is that our electrochemical area is clearly defined. So that semicircle is defined fixed area of our reaction surface. So we put the tape there, and that semicircle defines what is the reaction surface. And then we transfer that PDMS to the PU, the polyurethane. And then we deposit gold onto the pure urethane nanospike. So that pure gold-coated PU nanospike will be acted as our electrode. So that's our electrode surface. PU nanospike electrode with the semicircle surface is our reaction electrode surface. So you can see that's our setup of the experiments. And the SEM on the left is starting from the silicon mold, so that's the silicon SEM. And the right-hand side is after a few kind of transfer. First they transfer to the PDMS, and then the second transfer to the PU. So that's the PU SEM. As you can see that the nano-spiked feature has been very well preserved. So we deposit a layer of gold onto that nano spike, and then we use that as our electrode surface. So a few very basic characteristics to demonstrate that our nano-spiked PU electrode has a much better performance than flat PU electrode. So you can see from the left, so the middle two figure is the CV of comparison of the nanospiked versus the flat electrode. So as you can see that the red curve, which indicates the spiked electrode, has a much larger electrochemical surface area. So as you know that a larger electrochemical reaction surface area will allow you to bind more biomolecular, thus enable the sensor performance to be more sensitive. So that's the basic characteristic for the cyclophotometry, and that's the DPV curve for the same electrode. So you can see the signal strength is dramatically increased. And then this is the stability test. So we run a few. So that's 6 runs, and you can see that the current strength did not decrease, indicate that it's a very stable electrode surface that we are using. Further characteristic of the PU nanospiked electrode. So the left-hand side is the EDEX spectrum, so indicates the elements that we have for the electrode. So we deposit gold. So the chromium comes from the adhesion layer under the gold layer, so the gold can be very well attached to the polyurethane. So again, that's the CV comparison of the nanospike versus the flat. And after that CV, we calculate the electrochemical active area. So it's respectively for the red one, you have 0.13 around there, and for the black one, you have 0.07. So it's much larger, almost double the chemical reactor area for the electrode. So that's a kind of a basic CV, and we run that 50 times to indicate that even after 50 runs, it stays very stable. So because we are concerned after like transferring deposit of the gold layer, it might not be stable as the normal gold electrode, but after running 50 times, it demonstrates it's pretty good electrode surface. So again, we assemble the electrochemical immunosensor for the seed episode. So the surface assembly is pretty similar for the previous one. As you can see that it starts with A, which is the bell gold nanospiked electrode, gold-coated PU nanospiked electrode. So A, you have a pretty large current, and for the impedance, you have a very small impedance. So A start with almost a straight line. So as we add more molecular onto the gold surface, electrode surface, so we start with the systemine, then that's B, so the surface is kind of blocked a little bit, so that's B, that current becomes smaller, and more resistance is on the electrode. And then C, we attach the first single domain antibody for the toxin, so C is when we put on the antibody on the nanospiked electrode surface, and then you can see the surface is further blocked, and the current becomes smaller, and the resistance becomes larger. And then we put on the BSA to block the non-specific, to prevent the non-specific binding, and then we put on the toxin B. So as you can see that we did not add on the gold nanoparticle bind secondary antibody, which is different from the previous approach. And then during the toxin B binding, we optimize the binding time by looking at what's the current change. So to this, so that's the optimization of the experimental condition. And this is a comparison of nanospiked versus the flat PU spiked, a flat PU electrode. So that's PU nanospiked, and then we coated gold, and that's a flat PU electrode, and we coated gold. So you can see that BSA is one after block, and then after you put on the toxin B, you can see the current is about 6 times increasement after we do the nanopatterning of the nanospiked electrode. So that's basically the construction of the immunosensor. And we have the specificity test. We have like toxin B, you can see a very strong signal versus the other type of like similar protein binding. They have a much smaller signal, means that our sensitivity is pretty good. And then we also do the reliability or the stability, so we do it fresh, right, after the assembly, and then we do it again after 2 weeks. And that's within the range that we think that's pretty good. So that's the detailed performance of our new biosensor with the gold-coated PU nanospiked electrode. So it reached a detection limit of 0.5 picogram per milliliter, which if you remember the previous sensor is 0.6, and that's with the amplification of the gold nanoparticle bind secondary antibody. So even with the label-free method, we have reached 0.5 picogram. So the next step, we expect that if we further go on with the gold nanoparticle bind secondary antibody, the signal strength can be further increased. So that's a comparison of kind of similar approach. So that reference 13 is our previous approach, and that's the DPV that other people did. And and they have like a very tedious process of assembling the electrode and the electrochemical active tag. So that's point 7. The assembly process is multi-step, very tedious process, while our process is label-free, very simple. And also our nano electrode can be kind of batch fabricated, so you can, once you have a mold, you can use it over and over again. So it's a very simple approach. And after that is, if you are in, I think all the students know this, if you really want your sensor to perform, you have to go to the real sample. So we did kind of close the real sample. We get our stool sample from our collaborator of UMass Medical School, and then we do the kind of spiked. So we get the negative, like a stool sample, and then we spike the toxin into the stool sample, which indicates that the solution has all the other interference other than the toxin, and we achieved a pretty good selectivity for the stool sample. So this is under development still. This is our current progress. So our next step is to put down that sensor into acrylic microfluidic device. And this is from my collaborator, a professor in mechanical engineering. So they developed this acrylic microfluidic device so we can put our gold-coated TU nanospike electrode onto this acrylic microfluidic device, so that device can be disposable, like a one-time use, and you can, it's very cheap. So we have fabricated 3 electrodes on the PU-based electrode, and then we plan to put it, kind of clamp it into the PCB board, and then we can do the real C-deficit detection. So that's our current development. So we deposit the civil on the device, and then we are going to convert the civil into civil chloride reference electrode. So still some issues there, but it's under development. So that's the SEM of our current developed civil chloride, civil chloride reference electrode, and some kind of preliminary element analysis to indicate that we have civil chloride in our reference electrode. So that's our current kind of effort. So in this alternative approach, the summary, the bring away message is that our label-free, so keyword is label-free, electrochemical immunosensor for the C-deficit toxin has been developed. And this new sensor has achieved a detection limit of 0.5 picogram per milliliter. And this is expected to be able to fit into a disposable device format. So that's our like a single domain based, golden nanoparticle based, nano pattern electrode based for the C-deficit detection. So other approach, like besides the single domain antibody, which is a key component for the reliable, more adaptable biosensor. So Aptamer is kind of similar to the concept of the single domain antibody. Is another receptor that's very reliable, is fit to the long time preservation for the biosensor. So we have developed a few Aptamer technique, Aptamer combined with nanotechnology for the biosensor development. So Aptamer has the characteristic of stable, and it can be responded to all sorts of analytes, because whatever analyte you want to detect, we can synthesize the Aptamer to respond very specifically to that type of analytes. And nanotechnology, again, for the amplification, and when we combine these two, we have a very sensitive biosensor, and more importantly, we have the adaptable biosensor. So these are the previous kind of effort. And let's continue our challenges and opportunities. So as you have seen that we have demonstrated that we developed the surface plasma resonance. So the aptamer and nanotechnology combined, the method is the surface plasma resonance biosensor. So we have shown the surface plasma resonance electrochemical biosensor and more robust biosensor. So the next two approach that we present here is that we use advanced function nanomaterial together so it can overcome the diffusion limitation for the sensor development, the whole sensor development by magnetic field. So the solution here is to use very unique nanomaterials. So we think that we can use gold-coated magnetic nanoparticle for both surface plasma resonance detection and electrochemical biosensor detection. So we start with the magnetic nanoparticle because so sample and magnetic nanoparticle mixed, and then we have a separation process. So by binding specifically to the antibody bind magnetic nanoparticle, the target can be separated, which increase your downstream biosensor sensitivity. And then we put it downward for either SPR or electrochemical detection. So that's so this magnetic separation give you a faster process, high throughput point of care, and also very low volume, smaller size. So it's magnetic nanoparticle enhanced lab-on-chip system. So that's our synthesized magnetic nanoparticle, and we use that to develop the magnetic nanoparticle enhanced the surface plasma biosensor. So the top is for small molecule adenosine, and the next slide will be using the magnetic nanoparticle for immunosensor development. So the whole idea behind using the magnetic nanoparticle is that we want to have a unified design. So magnetic nanoparticles is the smart nanomaterial, and microfluidic system, which we can use magnetic field actuated magnetic system, so that we can achieve very fast, ultra-sensitive sensing microsystem. So that's our whole idea. So we start with mixing and separation and then detection. So we combine a lot of multi-physics. So we have the fluid mechanics, we have the reaction kinetics, we have the diffusion, like the mass transfer and magnetic field, all combined together to analyze the system. So that's a kind of example for magnetic nanoparticle enhanced separation. So we use multi-physics, we have the separation, involved fluid flow, and also involved the magnetic field actuation. So we look at what is the incoming fluid flow velocity, and we also optimize the particle size to optimize the whole separation efficiency. So that's our schematic design. So we look at the whole device to combine all the parameters to select the optimized separation parameter. So this is for the detection. So after we do the separation, we do the downstream biosensor, which is the detection. So again, it has fluid flow. So in this, we have the binding kinetics, and we have the convection diffusion governing equation. So that's the more of the mass transfer side. So we include all this, so you can see that, so these are the reaction surface, binding surface. So you can see the left-hand side is with the magnetic field actuation, and right-hand side is just passive diffusion. So you can see that with the magnetic field actuation, the reaction is, the binding is achieved much earlier than without magnetic actuation. So that's another comparison. So the first line is the just the fluid flow, And the middle dashed line is when I put the black body on the top of the channel, so it gives you some kind of mixing in the microfluidic channel to increase, to kind of overcome the diffusion limit. So that's a kind of a, people use that approach to overcome the diffusion limitation normally, so that's the middle line. So you can see that compared with the passive diffusion limitation versus the black body enhanced, it only increased about 7%, while the solid line is a magnetic field actuated surface binding. You can see that the time is shortened about 42%, which indicates that magnetic field actuation is a very effective approach to actually attract the target molecule onto the reaction site to shorten the reaction time. So that's our first part, which is the biosensor development, and a little bit on the nanotechnology enabled molecular imaging. So what we do is we do the carbon dots. So the synthesis is based on the milk. So we start with just a normal milk and turn that into carbon dots. So it's a very green synthesis method. And that's our distribution of the carbon dots we synthesize. And that's the cell viability test and imaging test. So it turned out to be a very effective approach for nanoimaging for the cells. So with that, I'd like to leave some time for question and answer. So I'd like to acknowledge all my group members. So my current group, so we don't have a large group now. I don't know what is the size of here. So I have a postdoc and a PhD student. And my past group member include 2 postdoc and 2 PhD. So also I'd like to acknowledge the National Science Foundation for the support of all this type of work. So a lot of the funding comes from the National Science Foundation. And with that, I'd like to conclude today's talk and
Any questions?
So it's a really nice talk. The modalities that you made, especially the nanoparticle-based modalities, you're focusing right now on this seeded facility toxin. But how have you tried to look at other potential targets, and it should be very adaptable?
Exactly. So so it's supposed to be a general platform that can fit into any type of binding. Yeah, we target with the Cdexter detection because we figure that after the more fundamental science, we want to see some real application. So the first target we focus is the Cdexter. Yeah.
I have a quick question with regards to the magnetic particles. How do you apply the magnetic field to something like this in containment?
Yeah, that's a very good question. So in our case, for the current approach, we use just the magnet to attract the nanoparticle onto the site. So if like designed more accurately, we can kind of do all the circuits so you can control the magnetic field much better and much stronger. Yeah.
When you look at the differential Voltron,
DPV, yeah.
yeah, cyclic, and then your method, the electroimpedance spectroscopy. Is there significant difference in time, response time?
Yeah, that's another very good question. Actually, we feel that actually, so for us, what we feel now, the DPV seems to be more reliable and react a little more faster. Yeah, even though the impedance is a very unique approach, but we currently feel that DPV is a more responsive and faster approach.
But in terms of when you're doing the measurements, I guess you have plenty of time. I mean, it's one of those, you take a sample and then you analyze it.
Oh, yeah, in terms of time, it's not that much different, but we just feel the DPV is more reliable because the impedance shows a more random behavior, yeah.
About how long do you think it would take to give a patient like an answer if they have using this test?
Yes, that's another good question because all matters for the portable sensor is the response time. So it depends on when you start to count that. So like because for our lab development, we start with all the incubation step. So if you count all of those together, it will take hours.
Mm-hmm.
But if in reality, after all this development, you can make everything pre-made, then the response time can be controlled down to minutes. Yeah. Yeah.
So with the nano spiking, your area enhancement seems to be about 2x,
Yes.
but the signal seems to be enhancing about 10x. So it's not linearly scaling with the area, you're getting some additional benefit, looks like, or?
Yeah, that's another point actually, because this is a newly published work. We have not kind of dig that deep into the rationality behind that yet. Yeah, that's a good point. Yeah, thank you.
I noticed the 4 nanoparticle is between 13 to 15 nanometer. How will you control the size to specific in that range?
Oh, for golden nanoparticle, for golden nanoparticle, the commonly accepted size when we synthesize, that's the normal range, 13 to 15 nanometer. If you follow the protocol of all the literatures, that's what people currently use for golden nanoparticle normally. Yeah.
I know usually the distribution will be a wide range if it's inside it. Is there a way like we can select a narrow range and just in the protocol we can control the range to be narrow?
Well, yeah, in the golden nanoparticle synthesis process, you have some like surface protection steps that you can control that a little bit better to make a little bit more mono dispersed rather than a large distribution. Yeah, definitely.
I have a question. So technically, when you're applying the polyurethane, and wouldn't you worry about microcracks? And how do you deposit gold on top of it? What's the method? And then wouldn't there be a possibility of microcracks that will affect the signal output?
Yeah, yeah, exactly. That's what we worried. So that's why we do the kind of 50 scans. So normally for any type of polymer, when you want to make the gold layer adhere better, you deposit first a chromium adhesion layer, so that gold can be adhered to the
Chromium.
Chromium. Gold can be adhered to the whole polymer base much better. So we do kind of experience some cracking initially, but after a few, we figure kind of optimization of the whole thing becomes better. So you can see after 50 scans, it's still pretty good. Yeah.
And your deposition method was using just the sputtering?
Yes, sputtering, evaporation.
Oh, okay.
Yeah, all of those works. Yeah.
Other questions? Well, let's thank Dr. Zhou one more time.